Hello, everyone, and welcome back. In this video, we're going to continue our discussion of methods of integration. And in particular, we're going to focus on the case now when your integrand is a rational function. That is, it's a fraction or quotient of polynomials. And the method that we're going to explore today is referred to as the method of partial fractions. What we'll do in this video is we'll introduce the general method, and I'll give you one simple example at the end. And then in the video that follows this, we'll continue exploring the examples that show the diversity of how to handle some of these problems. So let's get right into it. So the first thing that I want to start with is I want to think about how we add fractions. So this might be something that you learned a very long time ago, but of course we know that, say, if I give you 1/2 and we add it to 1/3, we can look for the common denominator here. So this would be 3/6 plus 2/6, leaving us with 5/6. Okay, so I hope that that is a very, very basic review, and it's not really that interesting. But if we think about the process here, typically, we're given something like the left-hand side where we want to add these things together, and we're asked to find the final product. Now, the reason I bring this up is because in the method of partial fractions, we kind of do this in the opposite direction. So for example, imagine I gave you this function, 5x minus 3 divided by x squared minus 2x minus 3. So you can think of this as your sort of 5/6. This is your final answer. Maybe you did a bunch of work and you got to this quotient. And this is a rational function. It's a linear function divided by a quadratic. It's polynomial over polynomial. But what our goal is here is to break this down into the atoms that build it. And so just like how 5/6 can be written as 1/2 plus 1/3, we want to write 5x minus 3 over x squared minus 2x minus 3 as its sort of 1/2 plus 1/3, as its simpler little atoms. So let's first start by emphasizing the factors. So just like how 6 is equal to 2 times 3, you have this prime factorization. Well, quadratics can often be factored into linear functions. So we can actually say that this is x plus 1 divided by x minus 3. And it turns out, if you do this properly, you can atomatize this, and you can say that this is 2 over x plus 1 plus 3 over x minus 3. Okay, that might not be obvious to you, but it might be a little easier if you start from the right and work to the left, right? Because now you're sort of doing that process of 1/2 plus 1/3 to get your 5/6. What we are going to focus on in this video and the next one is going in this direction. And let me show you why I want to do that. So for example, if I ask you to find the integral of 5x minus 3 over x squared minus 2x minus 3, that is a fairly intimidating function, and you don't really have a substitution that you can do here, right? If you try to substitute for the whole denominator, it's not going to knock off the numerator in an efficient manner. But we can use this sort of atomatization that we did, and this becomes 2 over x plus 1 dx plus 3 over x minus 3 dx. Now, if you'd like to, you can do some substitutions here, but you can very simply see that this first indefinite integral becomes 2 times ln of the absolute value of x plus 1 plus, and the second integral becomes 3 times ln of the absolute value of x minus 3 plus c. And so we were left with having to solve some really, really simple integrals that just wind up being a natural logarithm. Of course, the most difficult aspect of this process is asking yourself how to move from here over to here. And this is what's known as the method of partial fractions, this breaking up of these quotients in order to get these really simple factored components that can be integrated very simply. Now, let me illustrate the method using that quotient again. What we're going to do is we're going to take 5x minus 3 divided by x squared minus 2x minus 3. And just like I started with here, we want to identify the factors of the denominator. So we're going to write this in factored form first. So hopefully we didn't forget all of our basic calculus, remembering how to factor things. But then what we would like to do, the goal with the method of partial fractions, is exactly breaking things up into these simpler pieces. So we want some number, we don't know what it is yet. Imagine I didn't already tell you. So some number divided by the first factor plus some number divided by the second factor. And so now the question is, what are A and B that make this true? Well, now we can sort of work backwards. So it's kind of going to feel like we're going in the wrong direction. But this quotient right here, we can re-add it back together. So if we look for the common denominator, it's x plus 1 times x minus 3. So x plus 1 times x minus 3. And to get that, we needed to multiply the first fraction by x minus 3 on the top and bottom, and the second fraction by x plus 1 on the top and bottom. Now, let me expand this out. This gives me a plus b times x. And this gives me, let's see here, I get b minus 3a. And this is all divided by x plus 1 times x minus 3. Now let's compare. Look what I have right here, and look what I have right here. I have the same denominator, and if these things are truly going to be equal, I have to have the same numerator as well. So this would tell me that 5x minus 3 is equal to a plus bx, and then plus b minus 3a. So I try to put the brackets around each of the different pieces or the coefficients in front of the powers of x. And so now that I've organized things into powers of x, that tells me that the coefficient in front of x on both sides should be equal, which gives me that 5 is equal to a plus b. And similarly, the coefficient, the constant coefficient tacked on the end there gives me minus 3 is equal to b minus 3a. And now you can go about solving this, right? This is a linear algebra problem. It should be relatively simple. And you can find now exactly what I showed you above, that a is equal to 2 and b is equal to 3, which tells me exactly what I just saw. It tells me that this quotient becomes 2 over x plus 1. That was the a value of 2, plus b equal to 3 over x minus 3. So if you wrap this whole thing up, you saw how I determined the partial fractions, these little atoms, and then I use those little atoms to find an antiderivative. Okay, so there are much more complicated quotients that you're going to encounter while you're doing this. So let me provide you with the general method, okay? So this can be our roadmap or our general description of how to use the method of partial fractions, how you should be breaking up these quotients. And we'll use this in the last example we'll see today, and the examples in the following video for how to break these things up and evaluate integrals of rational functions. So the first thing is that if we're given, so say we're given f of x over g of x, we should have the degree of f is lower than the degree of g. Now, I'm going to show you an example in the next video of what happens when this is not the case. I'll give you a slight spoiler. We're going to have to do some long division. All right. So that is something that we probably are going to dread and we might have to seriously refresh ourselves with. But, you know, we're going to have to do it. So it's unfortunate maybe, but it's going to come with practice and we'll get good at it again. So this means in this case, the rational function is called proper, just like with fractions. Remember, there's improper fractions like 7/5, and there's proper fractions like 1/4, right? So it's the same type of idea. The other piece we need, so we need the factors of g of x. Now, this isn't always the easiest thing in the world, right? We're going to have to dig deep into the recesses of our brain to come up with all of the methods that we remember or have used in the past in order to factor these functions. Sometimes it's harder than others. In most of the cases that we're going to see, it's a relatively easy process. But, you know, I do not exclude the fact that, you know, this is not a generally easy thing to do. Now, luckily for us, there are a lot of computer programs now that can very easily find these factors for us, and sometimes we can take advantage of that. Okay, so here's the method of partial fractions. So what we want to do is, we're going to assume that x minus r stands for root, it's just some real number, is a factor of g of x. So r is a 0 of g of x. So suppose x minus r to the m, so this is an mth root, m could be any number, is the highest power. Of x minus r that divides g of x. Right, so again, this is just an mth root. It could be 1, or it could be 2, or it could be 3, depending on what g is, right? Then, to this factor, assign the sum of m partial fractions. And this is going to look like this. So this is, again, it's a complicated theoretical process, but we're going to see with the examples how to do this. Some number over the factor plus some other number over the square of the factor plus some number over the cube of the factor, all the way up to the highest factor that can be pulled out of this thing. So if this is a fifth root, right? So there's 5 copies of x minus 4 that can be pulled out of this thing. Then I'm going to have 5 terms in my partial fraction. A1 over x minus r, A2 over x minus r, A2 over x minus r squared, A3 over x minus r cubed, right? All the way up to A5 over x minus r to the power of 5. And you do this for each distinct factor of g of x. Okay, so I've got another piece that I want to talk about here, but let's just go back to our example. we had 5x minus 3 over x squared minus 2x minus 3. We saw that the denominator factors into x plus 1 and x minus 3. In both cases, m was equal to 1. So I had only one partial fraction coming from each one of those factors. Okay? Okay, so now let's think about another case. There are possibilities that you have complex roots. For example, you could have the function x squared plus 1 on the bottom. That thing doesn't factor over the real numbers. We are going to exclude ourselves from complex numbers in this class. So let's assume that you get a quadratic polynomial that can't be factored coming out of this thing. So let's let x squared plus px plus q be an irreducible quadratic factor. And so what it means to be an irreducible factor is that it doesn't have any real roots. And so this means so that x squared plus px plus q has no real roots. Again, think of x squared plus 1. Okay, and imagine you can pull out a bunch of factors of this, right? You could have more than one overlapping. So let's say, suppose that this thing, x squared plus px plus q to the power of n, you can pull out n of those. It could be 1 or it could be 50 for all we know, is the highest power of this factor that divides g of x. Then we're going to do exactly the same thing. So let me show you. So to this factor, assign the sum of the n partial fractions and it's not going to be as simple as case 1. In this case, you have a quadratic in the denominator. So we have x squared plus px plus q. And in the numerator, you're going to go 1 degree lower. So you're going to put a linear function up there. So b1x plus c1. Right? So in case 1 here, I had a linear factor. And so I went 1 degree lower, which is a constant. In this case, I have a quadratic factor. And so I go 1 degree lower, which is a linear function. So then I have b2x plus c2 over the second power of this factor. And just like in the previous case, I go all the way up to the nth power here. And here you have, again, a linear function over this, just like that. And you're going to do this for each quadratic factor of g of x. Okay, so now you're thinking to yourself, potentially, all right, Jason, is step 3, like if I have a cubic factor, then I have to do the same thing? No, right? This is not the case. And the reason for that is because we have a very, very important theorem in mathematics, the fundamental theorem of algebra, that tells us that every single polynomial can be factored into either linear or into linear and quadratic functions. So these are the only 2 cases that we need to care about, because we could take, a degree 70 polynomial and factor it into just linear and quadratic functions, just depending on if it has complex roots or real roots. Okay, so then what's step 3? Set the original function f of x over g of x. Again, it's assumed to be proper, equal to the sum of all these partial fractions. And then what we would like to do is we would like to clear the resulting equation of fractions and arrange the terms in decreasing powers of x. Okay, so we want to arrange this thing so we can work on it. And then we can equate the coefficients of corresponding powers of x in the numerator and solve the resulting equations for the undetermined coefficients from steps 1 and 2. Okay, so the process was basically illustrated to you with that example that I started with, right? It's essentially the same thing over and over here, trying to find these like A and B terms, just like I did with this process here. It's not easy to write out in plain English like this. So I know that the steps here can be intimidating. The most important of these steps, in my opinion, are steps 1 and 2. And that's because that tells you how you're supposed to actually factor these things and write out these little atoms, these little partial fractions that are going to be used to integrate this thing. So let me do an example to close this off, just to illustrate what I mean. So let's use partial fractions to evaluate this integral. So I'm going to give you the denominator already factored. In cases that we'll do in the following video, it won't always be factored. So we'll have to do a little bit of work. But imagine this is what I give you. So I give you a proper fraction of this form. And I want you to evaluate this. Now, in this case, you have linear powers they're only coming out. They're all real roots, and in this case, m is equal to 1 for all 3 cases. So the first thing that we're going to do is we're going to figure out what the coefficients are that go with these things. So we remember from step 1, we should have some number divided by the first factor, plus some number divided by the second factor, plus some number divided by the third factor. And when we write this all out, we need to recombine the right-hand side so that it's just one big fraction. And so we get this. And then in order to get the common denominator of all 3 of these terms multiplied together, the first partial fraction with an a has to be multiplied on the top and bottom by x plus 1 and x plus 3. The second partial fraction needs to be multiplied on top and bottom by x minus 1 and x plus 3. And the third partial fraction needs to be multiplied on top and bottom by x minus 1 and x plus 1. Okay, so this tells me that since the denominators are the same, I need to have the same numerators. So I have a numerator on the left-hand side given by x squared plus 4x plus 1. And on the right-hand side, I get a, and let me expand out x plus 1 times x plus 3. So I get x squared plus 4x plus 3. Let me expand out the factor in front of b as well. That gives me x squared plus, 2x. Minus 3. And the factor in front of c gives me a nice x squared minus 1. Now what I can do is I can organize things in powers of x. And so this gives me a plus b plus c times x squared. I get 4a plus 2b times x. And I get 3a minus 3b minus c in terms of the first power, or the 0th power, the constant term. So this tells me that the coefficient of, say, x squared gives me 1 on the left-hand side, and on the right-hand side gives me a plus b plus c is equal to 1. And the coefficient of x to the power of 1, so just x, gives me 4a plus 2b is equal to 4. The 4 is coming from the left-hand side where we have a 4x. And the coefficient of x to the 0 gives me, this gives me 3a minus 3b minus c, which is equal to 1. So now what you can see here is I have a linear algebra problem. Maybe you're learning linear algebra while you're watching this video, and you recognize this as a matrix problem. You can change this into a matrix, and you can try to solve this maybe with row reduction techniques. It's entirely up to you how you want to isolate and solve for A, B, and C. I'm not going to do it in this video just because it's time consuming, and I think it's something that we could do relatively easily. So let me just tell you that in this case, A is equal to 3 over 4, B is equal to 1/2, and C is equal to minus 1 over 4. Okay, so let me, now that I know what A, B, and C are, I've broken up my big quotient into partial fractions. So let's go back to the integral. We have this completely atomatized rational function. So let me start fresh here. This tells me that my integral of x squared plus 4x plus 1 divided by x minus 1, x plus 1, x plus 3 dx is the same as the integral of 3/4 x minus 1. So I'm leaving the 3/4 up there just so that we can emphasize that was A, okay? Plus 1/2, same thing, emphasize that was B, over x plus 1, and then minus 1 over 4 over x plus 3. The minus comes from the fact that c was equal to minus 1/4. And now these are easy integrals. These are all just natural logarithm integrals. So this gives me 3 over 4 natural logarithm of the absolute value of x minus 1 plus 1/2 the natural logarithm of the absolute value of x plus 1, and then minus 1 over 4 natural logarithm of the absolute value of x plus 3. And let's not forget it, this is an indefinite integral. We've got to tuck that plus c on the end. So that's the general process, right? This takes a relatively complicated looking rational function, and it atomatizes it. Remember, keep that example of 5 over 6 is equal to 1 over 2 plus 1 over 3 in mind. 2 and 3, those are prime numbers. This is a prime factorization of 6. And so what you're doing is you're taking a fraction with a composite denominator, 6, and you are turning it into a sum of fractions with prime numbers in the bottom, or potentially powers of prime numbers. This is the equivalent of doing that with functions of x. The prime numbers in this case become those factors, x minus r. So in our case, we had prime factors for the example we just did of x minus 1, x plus 1, and x plus 3. In the following video, we'll take a look at a bunch more examples, and we'll encounter some of the complexities that arise with this problem, while also showing how we can overcome them and how we can deal with these and how we can apply this method of partial fractions.